Hey guys, welcome to question 2 for the 2019 level 2 waves paper for physics. So question 2, fiber optic cables. Fiber optic networks are being installed throughout New Zealand to increase communication, effectiveness and efficiency. An optic fiber consists of core and cladding as shown below. The initial stage requires a beam of infrared waves to be sent through the fiber optic cable so it can be transmitted along great distances. The diagram below shows infrared waves traveling from the air into the core. Refractive index of air is 1 and then refractive index of the core is 1.45. Calculate theta 2 if theta 1 is 36 degrees. Alright, so this does follow the laws of refraction here. So n1 sine theta 1 equals to n2 sine theta 2. However, the very common mistake is that people forget that the angle that theta 1 is actually the angle of incidence. And the angle of incidence is actually the angle that the ray makes with the normal. As seen in the diagram, it tells you that this angle here is 36 degrees. However, this isn't the angle that the ray makes with the normal. This 36 degrees is the angle that the ray makes with the boundary, and that is not the angle of incidence. So this is not angle of incidence. So that means we have to manually find our angle of incidence first. So our angle of incidence, you know that this whole thing is 90 degrees. Hence, our angle of incidence must be 90 minus. So angle of incidence must be 90 minus 36, which is don't want to make a mistake here. Always make 54 degrees. So now we know our angle of incidence is equal to 54 degrees. And now we can apply our n1 sine theta 1 equals to n2 sine theta 2. So n1 sine theta 1 sine theta equals to n2 sine theta 2. So now we can just plug in our numbers. So refractive index of air is 1. So 1 sine 54 is equal to n2 is 1.45 sine theta 2 we're trying to find. So therefore we can have sine 54 divided by 1.45, and we're trying to find the sine inverse will be equal to our theta 2. So sine 54 divided by 1. So you should find that your theta 2, so theta 2 should be equal to 33.9 degrees. And that should get you in achieve grade here. Right, B. Name and explain the physics phenomenon that occurs at the air core boundary. So the physics phenomenon that occurs would be refraction, and this occurs because the ray is moving from a less optically dense medium, which is air, into a more optically dense medium, which is the core. Because it's moving into a more optically dense medium, then the ray is going to slow down, and because it slows down, it's going to bend towards the normal, and hence it will bend. So basically, that would be your physics phenomenon. You can say the phenomenon is refraction, and this occurs when a ray travels from refraction in general. We can say refraction in general is when the ray travels from one optically dense medium to a different optically dense medium. So you can say travels. How do I word this? And this occurs when the ray travels between two different optically dense mediums. You can say in this case, the ray is traveling from a less from a less optically dense medium to a more optically dense medium. And that would be the core. And you can talk about the ray slows down, which causes the ray to bend towards normal. And that will be your answer for this question. So this should be a merit level question. And to get an achieved, I think just this first statement here should be enough for an achieved. So stating refraction and explaining that's when a ray travels between two differently optically dense mediums. That should be an achieved. Alright, as the beam moves through the optical fiber, it is continually rebounding off the walls of the core, as shown below. For this to occur, the cladding must have a lower refractive index than the core. Name the phenomenon that allows this process and give a comprehensive explanation why it is important that the cladding has a lower refractive index than the core. Right, so as seen in the diagram, the ray travels in the core and it totally internally reflects back into the core. So this phenomenon is called total internal reflection, and this occurs when a ray is moving from a less optically dense medium into a more sorry guys, I got the wrong way around, didn't I? Very sorry, hold on. So it's moving from a more dense medium to a less dense medium. Apologies guys, I just had mind blank there. So when a ray is moving from a more dense medium to a less dense medium, the ray would reflect internally and then go back into the same medium. This can only occur when the angle of incidence is larger than the critical angle. So the critical angle is the angle of incidence when the angle of refraction is 90 degrees. That would be the angle of critical angle, and in order for total internal reflection to occur, the angle of incidence has to be greater than that critical angle. So name the phenomenon that allows this process. So you can say the phenomenon is total internal reflection. I'm going to abbreviate that as TIR. And this occurs when this occurs only when the ray is So the phenomenon is total internal reflection, and this occurs only when the ray is traveling from a more dense medium into a less dense medium, and when the angle of incidence is greater than the angle of critical angle. Okay, so now you can explain why it is important that the cladding has a lower refractive index in the core. You can say, it is important for the cladding to running out of space here. So it's important for the cladding to have a lower refractive index I'm going to continue this one at the back here. So it is important for the cladding to have a lower refractive index because if the cladding was more dense, then the ray would bend. Then the ray would bend towards the normal, and TIR will not happen. Sorry, it's a bit messy. The reason that it won't happen is because if for example, if I have a rough sketch of the diagram here, let's say we had so this is our cladding, and this here is our core. Let's say the cladding is more dense. Let's say for now this is more dense. Then what will happen? So this is our ray. This is our normal line. So if it is more dense, then this ray will actually bend towards the normal. So as this angle gets closer and closer and closer to the normal, then this angle of refraction will also get smaller and smaller. So basically, what I'm trying to say is that there's no way for the ray to actually reflect back into the core, because as the angle of incidence here decreases, if it gets smaller and smaller, it's going to bend closer and closer to the normal, and hence there won't be any total internal reflection. However, if the core was the cladding is less dense, then the ray actually bends away from the normal, and if it bends away from the normal, we can see that as this angle of incidence increases, then it's going to bend further and further away from the normal. So let's say this ray here. Say this ray here. Let's say this one bends here. If a ray traveling from here, it would probably bend. Oh, my drawings are terrible. Sorry. However, if a ray was coming from here, then it will actually bend. It will bend even further away from the normal. So it will keep bending further and further away from the normal, and hence you can see that eventually this ray will undergo the internal reflection, which is what the question requires you to do. So if the cladding was if the cladding was more dense, then the ray would bend closer and closer to the normal, and it will never actually occur the total internal reflection, because it will only get closer and closer to the normal. Right, so that should be all you have to say for this question. Not sure. I think this should be an excellence level question. This should be an excellence level question, and in terms of getting a merit, I think a merit can be up to here. It would be a merit grade. So if you get all the way up to here, then it will be merit. To get an achieved, okay, perhaps up to here will just be an achieved. If you only state one condition of the total internal reflection, you'll get achieved. If you state both conditions of the total internal reflection, you'll get merit. And if you explain all the requirements and why the cladding has to be less dense than the core, then you'll probably get an excellence. So D, the infrared waves have a frequency of 3.53 times. Alright, so D, the infrared waves have a frequency of 3.53 times 10 to the power 14 Hertz. The speed of light in air is 3.00 times 10 to the power 8 meters per second, and the refractive index of the core is 1.45. By first determining the wavelength of the incident ray in air, calculate the wavelength of the ray once it has entered the core. So the question, no doubt the question asks you specifically to find the wavelength of the incident ray in air. So that's something we need to find. So wavelength in air. First, we have to note down all the variables we have. So we have our frequency of the wave is 3.53 times 10 to the power 14 hertz. We have our speed in air is equal to 3 times 10 to the power 8 meters per second. And we also have our refractive index of the core. So our N2 is equal to 1.45. So we want to find our wavelength of the ray in air, and we have our velocity in the air as well as the frequency. You know that the frequency does not change once it has entered a different medium, so the frequency always remains the same. So hence we can use this frequency value and this velocity value to find our lambda for our wavelength in air. So we can say V equals to F lambda, and therefore 3 times 10 to the power 8 is equal to 3.53 times 10 to the power 14 lambda. And do a bit of calculator work, so 3 times 3 times divided by. So you should get that your lambda is equal to 8.4, and we can just round it to 8.5 times 10 to the power negative 7 meters. Alright, so now you can go to your formula sheet. You can use the relationship of N1 over N2 is equal to V2 over V1 is equal to lambda 2 over lambda 1. So so we're trying to find our wavelength of the ray once it's entered the core. So we want to find our wavelength 2. We have our wavelength 1 and we have our speed 1. So speed in air we have. So we need to try to work out our wavelength speed. Oh, actually, I just realized something. You can, oh sorry, no, not that much. Actually, you have your N2 and you also have your N1 because it's in air, so your N1 is 1.00. So now you can use N1 over N2 is equal to lambda 2 over lambda 1. So lambda 1 would be your wavelength in air because the incident ray in air and goes into the core, so your ray in air would be your lambda 1 and your N1, and your lambda 2 and your N2 would be your ray in the core. So we have this is our lambda 1. We found it's 8.5 times 10 to the power negative 7 because that's the incident wavelength of the ray in air. And we also have our N1 is 1 and our N2 is 1.45. So we can plug these numbers in. We can say 1 over 1.45 is equal to 8.5 times 10 to the power negative 7 over our lambda, sorry, wrong way around actually. We have our 8.5 times 10 to the power of negative 7 at the bottom and our lambda 2 we're trying to find at the top. So once again, we're going to use cross multiplication. So 1.45 lambda 2 is equal to 8.5 times 10 to the power negative 7. So just so you should get that your lambda 2 should come out to be 5.86 times 10 to the power of negative 7 meters. And that should be your final answer for this question. And this should be a merit level question. And with getting an achieved, if you find the wavelength of the ray in air, you'll get an achieved. Question 3, radio broadcasts. Mountainous regions make radio communication and signal reception particularly difficult. As a result, transmitters need to be strategically placed and use the correct frequency to ensure a signal is received. The transmitter shown below is set to broadcast through the region. Fred lives in the house between the two hills shown. He enjoys listening to old-fashioned FM radio stations. If a radio transmitter uses a frequency of 95 megahertz, show that the time period of the waves is 10.5 nanoseconds. So this M there, that's megahertz. Okay, so if you search it up, should just double check. Yeah. So a megahertz is represents million. So basically 95 megahertz would basically be 95 million hertz, and nanoseconds would be 10 to the power of negative 9 seconds. So this is some confusing units here, but mega, that refers to 1 million, and this nanosecond refers to times 10 to the power of 9 seconds. So we're going to be using our relationship of V equals to F lambda. So actually no, we do not need to use that. You'll use our relationship of our period is equal to 1 over F. So basically period equals to 1 over 95 times 10 to the power of 6. So 1 over 95 times 10 to the power of 6. So 95 million should be that do this. Okay, yeah, that's right. Okay, so you should get that your answer should be 1.05 times 10 to the power of negative 8 seconds, and that actually equals to 10.5 times 10 to the power of negative 9 seconds, which equals to 10.5 nanoseconds. I just realized I did everything in red pencil, but this should be an achieved question here. Right, so B, describe the phenomenon that allows the transmission to be received at Fred's home, despite the transmission tower being out of sight of his house. Include a diagram in the discussion and explain whether or not longer wavelengths will make reception of signals better for his house shown. Alright, so we know that if there's a longer wavelengths, then it's actually, if it occurs until it hits a obstacle, then it will actually diffract more than if it's a shorter wavelength. So considering if it's a gap size, for example, if we have a gap here, and if our wavelength is equal to or bigger than the gap size, then it will occur that's going to be a very large amount of diffraction, so that's a semicircular diffraction that's going to occur. However, if our wavelength is very small, then only minimal diffraction will occur. So you can say that longer, I can say when the gap size of the obstacle is greater than or equal to or greater than smaller than. Smaller than the wavelength. Maximum diffraction will occur, meaning the waves will bend more. If the gap size is greater than the wavelength, minimal diffraction, hence less likely to reach house. And I forgot about the first part. So describe the phenomenon that allows transmission to be received. So the phenomenon is called diffraction, and this is This is bending of waves when it hits an obstacle. Right, so we have to include a diagram as well. I was a bit confused by this diagram. So it shows that the waves are semicircular, so look. I drew it something like this, but a bit messy, but it should look something like this. So when it hits the boundary, it's going to diffract and it's going to bend towards the house, and the signal is going to be picked up. So in terms of the grade for this question, in terms of getting, I think this is a merit level question, and in terms of getting an achieved, I'm thinking if you can just describe what the fraction is, and I think that's actually enough for an achieved. And for a merit, I'm thinking you have to do both of these parts correctly to get a merit. A second transmitter broadcasting on the same frequency is built next to the opposite mountain to boost the signal. A test pulse is sent from each tower. Draw the resulting superposition after 3 seconds. Alright, so first things first, we want to draw where the waves are after 3 seconds, and we will see what superposition will be occurring. So, by looking at this first wave on the left first, so after 3 seconds is going to be 1, 2, 3 is going to be here. Just draw dotted lines for now. The pulse on the left, okay, so 1, 2, 3 is going to be this corner will be here. So hence this pulse will be here. Alright, so as you can see that the only area that's resulting in the superposition is this area here. And this area has a 4 block wave here and a 3 block wave here. So because this is in the same phase, constructive interference will occur, and hence the waves will add up, and hence we'll construct one stronger wave. So 4 plus 3 is actually a 7. So your resulting wave at this particular area will be 7 blocks high. So hence your final block should look something like this. So it should look 3, and then it goes 1, 3, 4, 5, 6, 7, and then back down to 4. Yeah, and that should be your resulting superposition, and this should be a merit level question. When a second transmitter transmitting at the same frequency is added, explain with reference to wave interference why some locations in the valley may receive a boosted signal, while other locations may not. Okay, so for this question, this is just one of the standard constructive and destructive interference questions. So I'm not going to write a whole essay, but I'm just going to cover the important points you need. So important points you need is talking about, in terms of the boosted locations, you can talk about constructive interference. And your path difference, you should talk about path difference. Your path difference in this case would be n lambda. In this case, you can say trough is meeting with a trough. Trough meets with trough, or crest and crest. And you also can say that the waves are in phase. Hence they add to create one stronger wave. So that's constructive interference, and hence you can say boosted signal. In terms of the unboosted signals, you can say it's destructive interference. Our path difference in this case would be not a whole number, so a fractional number, so n minus 1.5 lambda. We can say that trough meets with crest, and hence waves are not in phase. Hence the waves are not in phase, hence they might cancel out. And you can say this is diminished signal. Yeah, so those are the main important points you need to cover in your description. So constructive interference and destructive interference, path difference, what parts of the waves are meeting with each other, and whether the waves are in phase or out of phase, and whether the waves are adding to create a stronger wave or the waves are cancelling out each other to create one weaker wave, and how this links to a boosted signal or a diminished signal. And this, if you cover all 5 of these points, so all of these points here, that should get you an excellence grade. In terms of getting a merit grade, you can cover at least okay, you have to mention constructive interference and destructive interference no matter what. And you need to mention hence this one, and link it to boosted signal. That might get you a merit grade. And in terms of getting an achieved grade, if you can just say constructive interference or destructive interference, that could be enough for an achieved. Yeah, but I'm not too sure. Thank you for watching this video. I hope you enjoyed, and I hope to see you all in the next one. Thank you. Bye.